Hello, um, welcome to this video. I wrote some stuff out ahead of time. Uh, so I'm trying to get a better handle on physics, and I decided to learn. I'm focusing on electricity right now, and well, electromagnetism, and I decided to get a better handle on the units. They often say to um, check your work by making sure that your units make sense, but that's really hard when the units are so, it's often really hard to know uh, what the units you have in an equation turn into during the course of the equation. So uh, I've been learning the units in their, I guess to say in their component parts. That may not be entirely accurate from a theoretical perspective, but I think it's accurate. I think it's very helpful from a pedagogical perspective, and I think there's at least some truth to it, whether this breakdown is perfect or not. Uh, the other thing that I did, if you'll notice, if you were to look this up, you would see if how many of them I remember. So the standard units in physics are kilogram. Um, let's see, most of them you see here: kilogram, meter, second, amp, candela, and I'm pretty sure there's 7. 1, 2, 3, 4, 5. I'm missing 2. Yeah, let me look real quick. Kelvin and the mole. So candela, Kelvin, and mole do not relate to what I'm doing right now. Candela would be for brightness, Kelvin is for temperature, mole is for quantity. But these four would appear in my equations, except you'll notice you don't see any amps anywhere. So back up a second. Kilograms is mass, meters is distance, seconds is time, amps is current. And the issue that I had when I started learning these is I was like, why is amps the standard unit when coulombs makes more sense conceptually to be the standard unit? So I Googled it, and apparently many other students have the same question and take issue with the same thing. And basically, it comes down to two reasons: one historical, and the other one, well, they're both really historical, but it's historical in the sense of I think it was just done in the past, and so people just still stick with it. But it's also was mentioned that at the time that these standard units were decided, amps was the easiest to accurately define. So these 7 units are the ones that have definitions to remember. So kilogram is based off of a physical mass that's held somewhere, I don't know, probably somewhere in Europe. Meter has to do with the distance that light travels in a vacuum. Seconds, this one I don't remember. Maybe this one also had to do with light. Uh, to be honest, I don't remember most of the rest of them. Anyway, it's based off of these definitions. However, I chose to take these units and switch out amps for coulombs, and to be honest, they look a lot nicer too. Um, so let's go through these because I think it is very interesting. I don't think this is the only thing that I need to do to improve my physics understanding, but I think this is a helpful endeavor. And part of it is working from the fundamental units to the derived units, which is what I'm doing now. A lot of the units make sense, and they make sense in a couple ways. You can kind of see some hints as to conceptually what is going on with the unit, with the phenomenon. And you can also see some patterns as well as some tricks to learning them. So let's take and kind of highlight some patterns real quick. So you notice that a great deal of these have kilograms times meters in the top, or perhaps meters raised to a power. This one has it just has it in the bottom. So this one's like a flip. Let's write it on this side. Like a flip of quite a bit of the others. Kilograms, meters. This one just has kilograms. Kilograms, meters, kilograms, meters. Oh, it's almost all of them. I didn't realize it was that many. So that's one thing to notice. Another thing to notice, so you're taking mass times distance, or distance raised to a power in a lot of these. But so you're taking some mass value and you're multiplying it by some distance value, and it's very common throughout many of these. Another interesting thing to note is that kilograms over coulombs happens quite a bit. So here it does not happen. Here we have kilograms over coulombs, kilograms over coulombs, kilograms over coulombs. This is the reverse, kilograms over coulombs, 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 and then there's no kilograms over coulombs here. So that's interesting to note, and that's mass divided by charge. So that's conceptually that is the amount of mass you have per an amount of charge, or per an amount of charge squared in some of these. So you're taking the amount of mass per charge. That's in quite a few of these. And then maybe, I don't know, probably just one more thing here that I want to point out. Quite a few of these have coulombs times seconds, which here's where the difference would be. If you chose to use amps instead of coulombs, meaning current instead of charge, then you're going to just take and raise the seconds to another power, because amps is coulombs divided by seconds. It's coulombs per second. It's the flow of charge. So anyway, coulombs times second. It appears here, 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 but once again it's on the top instead of the bottom. Here, here, here. There's no seconds here, which is telling, and there's no coulombs in either of these. So that's very interesting. There's already this huge amount of similarities between them. Now let's go through and start to break these down. So this says kilograms times meters per second squared. So this is mass times distance divided by time squared. And if you you might notice here that this is kilograms is a unit of mass, meters per second squared is a unit of acceleration. So what we have here is mass times acceleration. Well, mass times acceleration, we know that that's force, and we know that the units for force is newtons. I'll circle it. So this is a newton. Now in this one you'll see that the only difference between these two is that this one has an extra coulomb on the bottom. So this could be mass times acceleration divided by charge. Well, mass times acceleration, as we just found out, is force. So this is force divided by charge. Force per charge is going to be the electric field. Which I guess I could just use the abbreviation. It's normally E. So force is a vector, acceleration is a vector, and electric field is a vector, to distinguish it from energy, which is not a vector. And yeah, so this one doesn't have actual standard units like a newton, like just a single unit, but the two common units are newtons per coulomb, which makes sense because we just said that mass, kilograms times meters divided by seconds squared is a newton, and then we're taking the newtons and dividing it by coulombs. The other one that's not so apparent yet is, I think it's volts per meter. Let me actually check that. Some of these I'm not as certain on. I'm pretty sure that's correct. Where did it go? Should be this one. Yeah, volts per meter. So these would be the two common ways to represent an electric field. Newtons per coulomb or volts per meter. The next one, you see mass times distance cubed divided by charge times time squared. Well, let's kind of tweak this a little bit so that we have mass times distance, and then we're left with distance squared. But distance squared is the same as area divided by charge times time squared. So, and actually, you'll notice when comparing this one with the one above it, it's the same except this one has two extra distances, so it has the area. So basically, this is the electric field times area. So mass times distance over time squared is acceleration. So mass times acceleration per charge is the electric field. The electric field times area is electric flux. So flux electric. And this, I also don't remember how they usually represent this in units, so they're saying volts times meters. So if you took the top one here and you multiplied it by meters squared, the meter on the bottom with the meter at the top would cancel and you'd have volts times meters. Or if you took the bottom and multiplied it by the other one and multiplied it by meters squared, you'd have newtons times meters squared per coulomb. So these are at least two standard ways to represent electric flux. And now you already see in the units the similarity in the relationship between these three quantities. Newton is mass times acceleration, which is force. The electric field is force per charge. And the electric flux is the electric field through through a surface area, basically through an area. I don't know, surface area. I guess I think through a cross-sectional area would be more accurate, but that part you don't necessarily get from the units, like you don't get all those details, but you can see that it at least has something to do with an electric field going through an area, because the units tell you that. All right, let's look at the next one here. We have mass, we have an area, we have charge, and we have time. So mass, listen, yeah, we'll do that. So this I don't mean to mean meters, I mean this to mean mass. Mass times area per charge times time. This one, let's see if I remember this one. We have mass. So we have something to do with a thing going through a cross section again, through an area. And it's like the mass going through the area per charge time. So almost like the mass through the area per time, but then we also have this per charge. I want to guess that this is a farad, but let me double check. No, I get this one wrong all the time. This one's a volt, this one's electric potential, which also has the same. So this V stands for electric potential, this V stands for volt. They both have the same symbol. And now this one, if I go back, we had volts per meter. So if we took this If we take this one right here, a volt, and divide it by a meter, we're going to have kilograms times meters per coulombs times seconds squared. Oh, wait a second. I didn't write this squared here. That was my mistake. Actually, I have it wrong on my flashcard. This is supposed to be seconds squared. Let me fix that real quick. Okay, so there's a volt. And volt, conceptually, a volt is a kind of a unit. Well, electric potential would be the more proper word, but that's kind of, I think, meaningless to a layperson. So something to put you in the right ballpark would be, it's kind of like electric pressure. It's the potential for the electricity to flow, I guess, which is kind of similar to thinking of the pressure is like the potential for water to flow. So this is the potential for electricity to flow. Let's see. Yeah, so we have, I don't know here, I'm sure there's a way to conceptualize these kilograms times meters squared per coulombs times seconds squared, but that one I don't have as good of a solution for. You could break it down into newtons per coulomb. Actually, electric field times distance, because kilograms times meters per second squared right here is newtons. Newtons per coulomb is the electric field. So the electric field times distance, I guess that has to do with the ability of something to flow. It's still not, this one's not quite as clear as some of the others were. All right, next one, we have coulomb squared times second squared over kilograms times meter squared. So here we have charge squared times time squared over mass times distance squared. And this one's might be more helpful if we end up thinking of it as the inverse of something. So this is another one I think that I don't have a good conceptual explanation for, but let's see what happens when we take kilograms times meters squared over top of coulomb squared times second squared. And then this would be to the negative 1. So we almost see the same thing as we just had. So kilograms times meters squared per coulomb times second squared is a volt. So this is volt per charge. So this is the inverse of volt per charge, which is the same as charge per volt. I should, if I'm keeping those consistent, this would be coulomb. Probably this down here should just, so this would be electric potential. Electric potential per charge. This is charge per electric potential, or coulomb per volt. And conceptually that one's not as clear, and I also don't have fully memorized this one. This one might be the farad. Yeah, this one's the farad, which is the unit for capacitance. And charge per volt. So I guess maybe what you have going on here is for each volt, how much charge do you have? So when you take a capacitor and you charge it up, it's like as you apply more volts to the capacitor, how much more charge are you getting on the capacitor? And I think that's going to at least be in the ballpark of a conceptual explanation of these units. Moving on to the next one. Kilograms times meters squared per coulomb squared times second squared. And you'll see that's what I had down here when I flipped this. So this is the inverse of what we just had. This is the inverse of the farad. Yes. So this will be volts per coulomb. And this one, if we have volts per coulomb, or electric potential per charge. Yeah, I don't remember this one either. This is resistance. So this is ohms. And I guess it makes sense that, I'd have to think more about that. Unless I made a mistake here, it looks like resistance is the inverse of capacitance. But this isn't supposed to be seconds squared. Okay, I was gonna say I didn't think that was right. So let me fix that. This is not supposed to be here. Alright, so we know this is this resistance now. And this one, we're going to have this kilograms times meters squared per coulomb squared, but this one's per second and this one's not. Let's come back to that. So this one's ohms. This one's easy. Coulombs per second, that's amps, which is current. It's a measure of current. And so this is how many coulombs flow through a cross-sectional area per second. Kilograms per coulomb times second is, okay, this one helps me because kilogram per coulomb, I think of like mass per charge, and I'm not really sure why, but for some reason that makes me think of a magnetic field. And this one is, let's see, what's the unit for, this is a Tesla, which is the unit for magnetic field. So this is the strength of the magnetic field. Just double check this. Yep. And then the next one, of course, you'll see that it's basically the same, except you're moving through this cross-sectional area. So this is like Tesla, Tesla times area. So this is a Tesla through a cross-sectional area, which is a Weber. And this is magnetic flux. So the flux ones are easier to remember if you do, if you solve surface integrals and calculate for flux, you'll see that flux is an integral through a surface area, basically. Okay, so this next one now, we see that this one is like ohms, but ohms is like this thing per second. And this one I don't remember. I think this is inductance. Yes, it is. So this is a Henry, because this is inductance. So conceptually this one's harder to think about, I think, but you have mass times area per charge squared. Yeah, that's hard to say. I don't know, but inductance and resistance is like inductance per second, which is very interesting. I didn't know that either. Let's look at the next one. Kilograms times meters squared per second squared. So this one is actually going to work for us. We'll see that this is equal to mass times, You could break this down a couple ways. You could say this is area and this is second squared. You could say this is distance times distance over second squared, and when you do that you'll see that the one distance per second squared is the same as acceleration. So we're going to say mass times acceleration times distance. That equals mass times acceleration is force times distance. Force times distance, that's work. So we've now reached work or energy. The unit for those is the joule. So kilograms times meters squared per second is the joule. And this is like kilograms through an area per second squared. I don't know, it's just interesting to think of it that way. But anyway, so this is a joule. This is what a joule is. Now, kilograms times meters squared. I wrote the same thing twice. One of these is wrong. That one's right. This is supposed to be seconds cubed down here. So you'll see this is the same as the one above, but with an extra second on the bottom. So this is the same as joules per second. So how much energy do we have flowing through something per second? This is going to be equal to power. So there you go. A lot of these, I think it's very helpful. The concepts become kind of clear when you flesh them out this way. Some of them were not quite so helpful, and maybe that's just because there's something that I didn't understand to explain, and further look will reveal some interesting thing about physical reality. But yeah, this is my little plan here, and once again, if you look these up, you'll see amp instead of coulomb as the base unit, and I don't know, I don't like it, because then when you try to think about them conceptually like I was doing, you'll find most of them make sense when you think about them conceptually, and they are a lot easier to think about if you use coulomb as the base unit instead of second. So yeah.